today, our mathematician spotlight is Rich Schwartz. Rich Schwartz was my PhD advisor. So in math, we talk about mathematical genealogy. So Rich is my advisor, so he's my mathematical father, and his advisor, Thurston, is my mathematical grandfather, and so on. So he's my mathematical father. He is Chancellor and Professor of Mathematics at Brown University, and he studies geometry and dynamical systems. So one of the things that he was doodling with in undergrad, I don't know if any of you like to doodle, but here's a doodle that Rich liked to do. He would draw a pentagon, and then he would make a star with the vertices. Okay, and now here you get a new pentagon. So here's this new pentagon. And then he would make a star with those vertices. And that gives you a new pentagon. And then he would make a star with those vertices. And that gives you a new pentagon, and so on. Okay, and so you can get all these smaller and smaller pentagons. And one thing about this doodle is that no matter how big your piece of paper you start with, or how fine your pen you start with, eventually it's too small for your page. But he wondered about these pentagons. So we have the green pentagon, and then the red pentagon, and then the yellow pentagon, and then the orange pentagon. And he wondered about the shapes of the pentagons. How does the next pentagon depend on the shape of the previous one? So for sure, if you start with a regular pentagon, all the pentagons after that will be regular. But what if you don't? And so he wondered about this starting in undergrad. But then by the time he got to PhD and to being a professor, he was able to work on it. So he used a computer. He uses a computer a lot in his research to sort of explore the system and figure out what the answer is. And then he was able to prove things about it. So he calls this the Pentagram Map. So this is the Pentagram Map. And while I was a graduate student, people actually got really interested in it. He wrote a couple of papers on it, and people were really excited about it. So something that you just doodle with now could turn out to be really interesting. Something else that Rich has done in the last couple of years is he started writing children's books. So children's books about math, like really good children's books about math. His first one was about prime numbers. His second one was, well, actually the next three have all sort of been about infinity. The second one was about really big numbers. That's my favorite. And then the next two have been about infinity. So did you ever say as a kid, like I'm infinite awesome, and then the other person is like, well, I'm infinite plus one awesome, you know? And the idea is like, how do you explain to a kid that infinity plus one is the same as infinity? So here's this book, Rich just wrote it. It's called The Infinite Farm, and here's how he explains that. So we have it here. We have Gracie. Gracie is an infinite cow, and she loves shoes. She has a pair of shoes on every foot, and her feet go on forever. So she has infinitely many feet. But her friends know that she likes shoes, so sometimes they give her a new pair of shoes. Here's the new pair of shoes here. How can she put on her new pair of shoes and also wear all of her old shoes? Well, she stands on an infinite sticky strip, takes each of her feet out, and just moves one forward. So she ends up having a pair of shoes on all of her feet again, but she still has the same number of feet. Infinity plus one is the same as infinity. Of course, he doesn't talk about infinity plus one equals infinity. He just talks about the cow. So I think it's really cool. Okay. So cool, right? And such nice pictures. I think they're not just good for teaching like 6-year-olds about infinity. I actually really like his explanations enough that I would use them to teach college students about the same ideas. I suggest his books as optional extra texts for the course, because he explains it in a really good way. Yeah. Okay. All right, let me turn that off. So last time we talked about limits, and today we're going to talk about derivatives. So as a review, in single variable calculus, you have some function, like here's y equals f of x, and you care about the derivative of the function at some point. So maybe this is a. And you want to know what's the derivative of f of x at a. Well, that's just the slope of the tangent line here. So the slope here is just f prime, the derivative of the function evaluated at a. That's what the slope is there. And one thing you might want to do is write an equation for this tangent line. And the equation for the tangent line, which maybe I'll call L of x because it's a linear thing, so linear, L for linear, is just the value of the function. So whatever this value is, this is f of a. So it's the value of the function f of a plus the slope of this line times how far you are away from a. So f prime evaluated at a times x minus a. This is like point slope form. You have like y minus y1 equals m times x minus x1. But I put the y1 on the other side. And I like it in this form because it says what I just said. The value of the line at any time, the y value of it, is the y value you start with, f of a, plus the slope of the line times how far you are away from a. And this might be positive or it might be negative depending on which side you are on. Okay, so our goal is to generalize this and push it up a dimension to multivariable functions. That's the dream. So let's do it. Oh yes, because Rich is from Brown, I'm wearing my brown shirt. So forgot to do that. Mathematics at Brown University, a good thing to do. And because Rich is studying the Pentagram Map, which has lots and lots of pentagons in it, I wear all the pentagons. Good, okay. Uh-oh. Sorry. All right. Okay, so multivariable functions. In single variable calculus, we have a curve. And in double variable calculus, we have a surface. So I'm going to draw my surfaces sort of like a lump here. So this function here is z equals f of xy. So you imagine that down here, we have the xy plane. Maybe this is the positive x-axis, and this is the positive y-axis. Okay, and we are interested in finding the tangent plane now instead of the tangent line at some point. So maybe this point is sitting above the point A, comma B in the plane. And we want to know what's the sort of the tilt of this surface at this point. So the way we deal with that is we find this slope in two different directions. So the first thing we do is we say, well, what if I went just in the positive x direction? So if this is like a map of of my mountain range, I want to walk just in the positive x direction, so that's like east. Well, up here, that looks like walking along the surface along this line, and I want to know, right at my point, how is my elevation changing? So what is the slope of this if I walk in the positive x direction? So here's the slope in the positive x direction. We have notation for that. It's the partial derivative with respect to x. And if we're asking about it above the point AB, it's at AB. And equivalently, there's equivalent notation in partial derivative f with respect to x evaluated at AB. Okay? So that gives you a slope in one direction. But that doesn't uniquely determine how things are tilted there. We also have to find the slope in the other direction. So suppose you were going to walk in the positive y direction, or north. Well, we can draw the curve of what it would look like to walk through this in the north direction. And so we have also the slope in this way. So this is the slope in the positive y direction. And our notation for that is the partial derivative with respect to y evaluated at AB, or the partial derivative with respect to y evaluated at AB. Okay. So our idea is instead of just taking a slope of our single function, we'll sort of slice our surface. So if we slice it with a vertical plane that cuts through this blue curve, we get just a one-dimensional curve, just like a downward sloping parabola maybe. It's like a single variable thing. So we can take its slope. And then if we slice it perpendicularly with this red plane, we get this red cross-section curve, which is again just a single variable thing, so we know how to take its derivative. So we can find the slope in both of those directions. That's the idea. Yeah? Yeah, question?
So when you're taking the derivative with respect to x, for instance, you assume that y and z are constant, and you just take the derivative function with respect to x.
That's right. When you take the derivative with respect to x, you treat y as a constant, and just take it with respect to x. So let's do an example. So find the partial derivatives of the function f of xy equals 5 minus x squared minus 2y squared at the point 1, 1. This is our dream. Okay. So first, let's take the partial derivative in the x direction. And it's always the positive x direction. So like you're going north. So if we are here at our point 1, 1, walking in the positive x direction, then y is always equal to a constant. Y is always 1. So we can use f of x comma 1 because y is always 1. So let's rewrite that. That's 5 minus x squared minus 2. So that's just 3 minus x squared. So what we've done here is we've written an equation, actually, for this blue downward sloping parabola. We've taken a slice when y is equal to 1 of this surface, and we get this blue downward sloping parabola 3 minus x squared. Z equals 3 minus x squared, and y is always 1. So now we want to know what's the slope at the point x equals 1. Well, we can just take the derivative and plug in. So let's take the derivative with respect to x of this function. Can you take the derivative with respect to x of this guy? Yeah, negative 2x. And at x equals 1, we would just get negative 2. So that tells you that if you were at this point on the surface, walking in the positive x direction, your slope would be negative 2. It's reasonably plausible from this picture. Certainly the blue looks kind of down. Negative 2. Okay? Okay. So now, how if we want the partial derivative in the positive y direction? Okay, now we're looking at this pink curve. So we are standing at 1, 1, and we're going to walk in the positive y direction. So x is constant, always equal to 1. And then we get this downward thing. So let's see what we get. So we get f. X is always equal to 1. And so f is just a function of y. So let's plug in 1 here for x. We get 5 minus 1 minus 2y squared, which is 4 minus 2y squared. So that is exactly the equation for this downward sloping parabola. It's z equals 4 minus y squared, and x is always 1. That's the idea. We're just taking a slice of this three-dimensional thing and getting a function of one variable. Okay, and let's take its derivative. So the derivative with respect to y of f of 1 comma y, the derivative of this thing with respect to y, negative 4y, and at y equals 1 is negative 4. So that tells you that if you are walking in the positive y direction, your slope would be negative 4. Pretty plausible. Yeah. Okay. Yeah. Okay. So I did this with explicit numbers and plugging in, so that you know that we really are just taking slices of this holding the other variable equal to a constant. But in practice, we don't usually actually plug in these numbers like this. So in practice, meaning what you would actually do on a daily basis, like in your homework or every day other than right now. In practice, just treat the other variable, whatever one you're not taking the derivative with respect to, as a constant. So here's what we would do. So we have our function of xy, which is 5 minus x squared minus 2y squared. OK, and we want to take the derivative with respect to x. OK, so you say, I want to take the derivative of this thing with respect to x. Let's do it term by term. The derivative of 5 with respect to x. 0. The derivative of negative x squared with respect to x. Negative 2x. I'll write that down. The derivative of negative 2y squared with respect to x. 0. Yeah, because with respect to x, y is just a constant. Because if we move in the x direction, y is not changing. It's just a constant. So, and you can also think of it as like if we had plugged in some other number other than 1 here, even if it was a million, when we took its derivative, it would have been 0. OK, and then similarly over here, if we want to find the partial derivative with respect to y of xy, derivative with respect to y of 5 is 0. Derivative of negative x squared with respect to y, also 0. Derivative of negative 2y squared with respect to y is negative 4y. So that's what you would do. And then if you wanted to know what it is at a specific point, for instance, if you want to know what's the partial derivative with respect to x at the point 1, 1, and what's the partial derivative with respect to y at the point 1, 1, well, you just plug in. Here, x is 1, and y is 1. Y doesn't appear, but that's OK. X is 1, so this is negative 2. Over here, x is 1 and y is 1, so this is negative 4, which is exactly what we got before. We got negative 2 and negative 4. So we get them again. Yeah. Yeah, questions or ideas? Question?
Are we about to see how to construct the tangent plane?
Yes, we will see how to construct the tangent plane as soon as we practice just a little bit more with partial derivatives. Yeah. OK. So we'll do an example of another partial derivative. But before we move on, I just want to tell you about notation. So there are a couple of different notations that mean the same thing. So we can say, for example, the partial derivative of f with respect to x in this notation. And that emphasizes that it's a function. It's a function of x and y. Because it is. The partial derivative is a function. The slope in the x direction depends on where you are. Different places, the slope in the x direction will be different. On the other hand, we sometimes like to emphasize that it's kind of like a ratio, kind of like a rise over run thing. And so sometimes we can use this notation, partial derivative of f with respect to x, evaluated ab. It means the same thing. And so these are all partial derivative of f with respect to x. I'll tell you something it's not the same as. It's not the same as df dx. When you use a d like this, a regular lowercase d, it means the total derivative of f with respect to x. So this is total derivative of f with respect to x. So you use this one when f is just a function of x, like f of x equals x squared or f of x equals cosine x, when f is only a function of x. But when f is a function of more things, like maybe a function of x and y, you use a partial derivative of f. Now you all know how to make a d, because you learned to make that a long time ago. But this is new. This is del. So if you would, take your writing utensil or your finger. Here's how you make it. First, you go around the bottom like this. And then you go around the top like that. Yep. This is del. Ready? Say hello to Adele. Good, right? Okay. Okay, so this is del. And now you've met. Good. Okay, so let's practice partial derivatives. So for instance, suppose you have the function g of xy equals x squared plus x squared times y plus e to the x times sine of xy. Your quest is to take the partial derivative with respect to x, and maybe also with respect to y. Remember, these are functions, it's calculus, so the product rule, the chain rule, quotient rule, they all still apply. Okay, please do it and discuss with the person next to you. Okay, so it looks like a lot of you are done or at least paused, so can you explain how to do it? Yeah, go up there, pick up a piece of chalk, explain all the parts.
Hello, everyone. So basically, just taking the derivative of x squared times y with respect to x. Y is kind of like a coefficient, so you pull that out, and then the derivative of x squared is 2x. And then we'd have to use the product rule here, since both of these functions are dependent on x. And so the product rule means that we have to take the derivative of one of these functions times just that function, and then we'd switch and add. So the derivative of e to the x is just e to the x, and then times this function. And then we would add now the derivative of this function times e to the x. So the derivative of this function is just cosine xy. And then we'd have to use the chain rule. So y is just a constant, it's a little coefficient. So we pull that out. And that would be our answer. Is that right?
I think so.
Okay.
Yeah, very nice. Nice job. Yeah, very nice. Nice job. Yeah. Oh, yeah. Okay. Good. Great. So it might be a little fast for you the first time, but you'll have many opportunities to practice doing it step by step and treating one as a constant. It may be a little bit funny to think of e to the x as being a constant. Okay, we haven't done the second part yet. Let's do the second part. So how about the derivative with respect to y of this thing? Let's see, just x squared, because that's y is our variable. This is a constant. And then with respect to y, e to the x is also just a constant. And then this is a function of y, so cosine of xy times the coefficient on the inside, which is x. So it might be a little strange to think of x squared as being a constant and think of e to the x as being a constant, but with respect to y, they are. So, yeah, cool, okay. And these are functions of x and y, which tell you the slope going in each of the directions depending on what point you are at. Yeah. Okay, so now that we know how to take partial derivatives, it's just basically like regular derivatives, just you treat the other variables as a constant. We are ready to make a tangent plane. So let's go back over to here. So So suppose what we want to do now is we have this surface, we have the point that we're interested in, and we want to find the tangent plane to this surface at the point that we're interested in. So this tangent plane that just barely touches the surface there. That's the dream. Okay, well, in order to make the equation for a tangent plane, we need a point on the plane, which we have here. This point here is A, comma B, comma, whatever the z value is here, so f of AB. And we also need the normal vector. That's how we get our tangent plane equation, is use the normal vector. So in order to get the normal vector, we're going to take the cross product of two vectors that are parallel to the plane. So that's the idea. But the hard part is going to be constructing this normal vector, and we're going to use these two vectors that are parallel to the plane. So here they are. So a vector parallel to the plane in the positive x direction is, I claim, 1, 0, partial derivative with respect to x evaluated at that point. Okay, so that is actually this blue vector. So this is this blue vector or something in its direction. Maybe I didn't make it exactly the right length, but it's something in this positive direction, in the direction of this blue vector. Okay, here's the idea. So first of all, if we're going in the x direction, the y is not changing. So the y coordinate of this is 0 because y is not changing if we're going in the x direction. Okay, then I claim if you go 1 over in the x direction, that your z changes, goes up or down, by the partial derivative with respect to x there. Because it's just how much you go up. Yeah, exactly. So it's like, we call this the slope in the x direction. So it's like rise over the run. So if you run a distance of 1 in the x direction, you rise, or fall, a distance of this number. So that you basically just put your slope here, 1 comma partial derivative with respect to x. So that's where these come from. This is just like the slope. They go there. Yeah. And then similarly, a vector parallel to the plane in the positive y direction is 0, 1, partial derivative with respect to y evaluated at AB. For the same reason. So this is essentially the red vector. Since we're moving in the positive y direction, x isn't changing. So that's why this is 0. And then this just says if you do a run of 1 in the y direction, your z value changes by this much. So this is like the slope together. Yeah. So to write the tangent plane, equation, we need two things. We need a point, and we need a normal vector. So our point is just going to be this point that we know, a comma b comma f of ab. And then to get our normal vector, we'll take the cross product of these two guys. So we'll take 1, 0, fx evaluated at AB cross 0, 1, fy evaluated at AB. That's the plan. Okay. Okay, so let's just do it. Okay. So let's define the normal vector. We'll take the cross product. So the normal vector is the cross product. Okay, to write out a cross product, we do I, j, k, and then we put these as the rows. So we get 1, 0, partial derivative with respect to x, evaluated at AB, and 0, 1, partial derivative with respect to y, evaluated at AB. Okay. Okay, let's do it. So we are going to treat this as a 3 by 3 matrix and cofactor expand across the top row. So we get I times the determinant of this matrix, so 0 minus partial derivative with respect to x, so just minus partial derivative with respect to x at AB. And then it's plus minus plus if you're doing cofactor expansion, so minus j times the determinant of this matrix, so 1 times partial derivative with respect to y minus 0, so partial with respect to y evaluated at AB, plus k times the determinant of this matrix, which is just 1 minus 0. So just 1. So we can write out our normal vector. It's just minus partial derivative with respect to x at AB minus partial with respect to y at AB 1. Okay, so there's our normal vector. Okay. I don't have a lot of geometric intuition as to why this should be the case, but I do have a lot of geometric intuition about these two vectors. And then we just take our cross product and get this guy. Okay. Okay, well that's the first step. Let's write an equation for the plane. So recall that if the equation for the plane through the point x naught, y naught, z naught with normal vector a, b, c is, there are several different forms to write it in, but the dot product form, which might be the easiest to remember, is a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And remember, this was just a vector on the plane. X minus x naught, y naught minus y naught, z minus z naught is some vector that sits in the plane. And then ABC is perpendicular to the plane. So we just take the dot product of those things and set it equal to 0. That's where it comes from. Yeah.
Is the explanation for that in your notes on day 1 or 2?
Yep, day 1. Yeah, that comes from day 1. That's right. Okay, so we have used this. And let's now plug in. So for us, we use our normal vector here. So A is the first component here. So minus partial with respect to x evaluated at AB, that's our A, times x minus whatever our x naught is. And our point is A comma B comma f of AB. So this is just A. Plus B, our B is the second component here. So minus partial with respect to y evaluated at AB times y minus the second part of our point, so that's b, plus the third component, which is 1, times z minus whatever the z value is of our point, so that's f of ab, equals 0. So we just plugged in our coefficient and our point into this equation. This is a perfectly good way of writing it. But it's a little bit more elegant if we move things around. So I want to have z on one side and all the other stuff on the other side. So if we rearrange this, we get z equals f of ab plus this first term, partial with respect to x evaluated at ab times x minus a, plus the second term, partial derivative with respect to y evaluated at AB times y minus b. Okay. So that is the equation for the plane tangent to the surface, f of xy, above the point a comma b. Yeah.
And we don't have the terms that's like the derivative with respect to x of the constants because they're all 0, right? So it's just, is it just an algebraic thing? Like if we were to expand everything out, we would have a term that's like the derivative with respect to x of a, which is should be 0, right?
The derivative with respect, you have a term of the form the derivative with respect to x of a.
So like when you did the rearrangement,
Yep.
You probably went through like a bunch of arithmetic things, you know? And like one of them involved like just expanding everything, right?
Well, I just took actually these pieces. So this piece, this is the only piece that I multiplied out. So here I put z on the left. We kept z with the positive. And then I moved this 1 times f of ab over to the right. So this term here went to right there. And then I simply just took this whole thing and moved it over to the other side. So minus partial with respect to x, this whole term just became a positive on the other side, and that's this term. I actually didn't multiply it out. And then this entire term here went to here, just with a positive sign. Yeah. I like this form because it looks actually very similar to the tangent line equation. So it says you start with the value at that point, and then this is how far you moved in the x direction. However much far you moved in the x direction, multiply it by the slope in the x direction. However much far you moved in the y direction, multiply it by the slope in the y direction. So that's exactly like point-slope form back over here in one dimension. We said the value on your line is equal to, well, the starting value where you start, f of a, plus however far away you are from a times your slope. You can see this is exactly the same as the first, well, this f of a plays the role of f of a comma b. And then this is like slope times distance away for x. And then since we have two variables, we also have slope times distance away for y. So it's exactly the same thing. Just one dimension up. Yeah. So I think we should do an example for sure. One thing that I want you to notice, is that this here, f of ab, is a number. It's just, the height of your plane at that point. The partial derivative with respect to x at ab, also a number. So we have had that to be like -2 in the past. A, also a number. Partial derivative with respect to y, a number. And b, a number. So most of these things are numbers. The only things that aren't numbers are just x and y. So we're going to end up getting a linear thing at the end, so it's going to be a plane. If you end up with an equation for a tangent plane and it has some things like squares and cosines in it, something has gone wrong. Maybe you forgot to plug in your constants, because you want a linear thing at the end. Okay, so let's do an example. So find the equation of the tangent plane to, let's call it z equals 5 minus x squared minus 2y squared at the point 1, 1. But this is in 3 dimensions, so I need a third component. So if you plug in 1 here for x and 1 here for y, I think you get 2. 5 minus 1 minus 2 is 2. So at 1, 1, 2. Okay, that's what we want to do. So we have, this is our function, f of xy. So f of xy is 5 minus x squared minus y squared. So let's get all of our things. So we're going to need f of ab. We're going to need partial derivative. We're going to need a, and we're going to need b. We're going to need the partial derivative with respect to x at our a and b, and so on. Okay, so let's plug in. So f, what is a and what is b in this case?
1
Yeah, 1 and 1, because our point was 1, 1, function. So 1 and 1. So f of ab is f of 1, 1. And if you plug in those, you get, do you get? 2. I'm missing a 2. 2y squared. You get 2. Okay, the partial derivative with respect to x as a function of x and y is -2x. And so the partial derivative with respect to x at 1, 1, our point of interest is -2. And the partial derivative with respect to y as a function of x and y is -4y. And when we plug in the point we're interested in, it's -4. So we had gotten these before when we were practicing taking partial derivatives the very first time, a couple of minutes ago. So let's plug this in. Our z is f, so z is f of ab plus partial with respect to x evaluated at ab times x minus a plus partial with respect to y evaluated at ab times y minus b. Okay, so let's plug it in. So f of ab, 2. Partial with respect to x at our point AB. Negative 2 times x minus a. A is 1. Partial with respect to y at AB is negative 4.
Negative 2? Like,
Ah, you are so right. Negative 2. Good. Negative 2. Okay. Good point. Wherever you are. Great. Okay. And then the partial with respect to y is negative 4. And then y minus also 1. Okay. And you could call this z, but I might also call it the linearization of the function as a function of x and y. Because that's what it is. It's the best linear approximation to the function. So this is a perfectly good answer. And if you want, you can also simplify. I think we get 2 plus 2 plus 4 is 8 minus 2x minus 4y. Yeah, question?
Can we geometrically say that the plane is centered around the points A, B, and F, A, and B, or is it any point on the plane that can define that plane?
So we could have found the tangent plane at any point, but we chose to find it, the tangent plane, at the point 1, 1, 2.
So the plane is centered.
The plane contains that point. The plane is tangent to the surface at that point.
Got it.
We could have found it at any other point, but based on our picture here, it looks like that tangent plane isn't going to be a very good approximation anywhere else. Probably for this surface, that's only the tangent plane at that one point. Any other point would have a different tangent plane. Yeah. Okay, and the last thing I'd like to talk about is how this is the best linear approximation to the function at this point. So for single variable calculus, the best you can do is you can match the value of the function and you can match the slope. That's what a line does. Here, the best we can do is match the value of the function and the slopes in both directions, so both partial derivatives. So let's check. So the idea is that the tangent plane, whose equation is maybe L of xy, is the best linear approximation of f of xy at this point, so 1, 1 in our case. So let's check. So we have L of xy is 8 minus 2x minus 4y. We'd like the value of this to be equal to the value of the function at 1, 1 and the partial derivative. So let's check. So L of 1, 1. Can you plug it in? What is it? It's 2, okay? And is that the same as f of 1, 1? Yeah, it is. Okay, that's equal to f of 1, 1. Yay. Okay, how about the partial derivative of L with respect to x as a function of xy? Or actually, at the point 1, what's the only place we care about? Can you take the derivative of this with respect to x? It's minus 2. Yeah, it's actually minus 2 everywhere. So minus 2. And is that the same as the partial with respect to x? There, yeah. That's the same as the partial with respect to x at 1, 1. So that's good. That agrees. And finally, the partial derivative with respect to y at 1, 1. Can you take the partial derivative with respect to y? Negative 4. Yeah. And is that equal to the partial of f with respect to y? Yes, it is. So that's the idea. That's what this performs. It matches the value of the function and both of its derivatives. And that's what it does. And it also finds the tangent plane. Okay, thanks, guys.